Okay, can you hear me okay? Okay. So this is because I spent a lot of time making this animation. So I really want to show it for no reason. And let's just admire it again. Okay, so that's it. And again, so that's sort of the plan for this week. And I want to emphasize, of course, it's a quite biased selection. I can't possibly talk about all of these in detail. So the kind of physics I talk about is heavily biased towards what I know well and have been working on. Okay, so this I really just want to show that, we mentioned that these are sort of the parameters that control oscillation phenomena. And I think this is a great plot that sort of summarizes the experimental progress of these parameters. So this is existing measurement go from, the 2000s, which is sort of where I think it's fair to say that's where the oscillation framework has been established, to 2000. As you can see, a lot of progress made around 2010. So it was a very exciting time. I also want to show what's kind of like the level of progress into the future. So this figure is a couple years out of, actually a few years outdated. But roughly speaking, where the dashed line is, that's like right now-ish. And you can see the level of precision improvement that we'll get with the next generation experiments. In this case, we consider Dune, Hyper-K, Juno. So you can see, so quite a bit more precise in terms of measuring really pin down the PNS matrix. I do want to make a comment. If you can see the last row, last column, there's a little small black error bars. So those are actually the current experimental measurement precision for CKM mixing. So you're familiar with CKM mixing. It's essentially a PMS matrix in the quark sector. And I was quite surprised to see that by the end of next generation experiment, we're actually able to sort of reach comparable precision in neutrino sector with present day quark sector measurements. Right, so that's just to show the precision. What I wanted to show is the figure that we talk about in the morning, but I just want for you to see these color schemes really. So this is the famous snow measurement that has pinned down the solar neutrino fluxes. This quite famous and always use this color scheme. And this is the atmospheric measurement from Super-K. Again, so they always separate their sample, their plots like E-like, which is supposed to be, nu E. And you see the data points are sort of on top of the line, so that means there's no oscillation for nu E. And for the mu-like sample, sort of the shady things are the theory prediction of the flux with no oscillation. And you see the data clearly shows that on the right, things sort of agree. And then on the left, things start to disagree by like a very big factor, like a factor of 2. So that's the Super-K plot. So I mostly just want to show these two. And there's really no good place for me to talk about this experiment because it did not get built. But this is definitely the coolest experiment I personally have seen. So I just really want to talk about it for, again, no reason. Okay, so I said that, for the solar experiment, that's very, very early. That's in the 60s. At that time, we, didn't have that many ways to measure neutrinos. And so this was a proposed experiment by Frederick Rennes, and in the 50s. So this is even before the solar neutrino measurement. At that time, we really didn't know how to measure neutrinos. And this was a proposal, which was, here goes the following. So what makes neutrinos? Nuclear bombs. So then that's what the sphere indicates. So you see there's a fireball, there's nuclear explosion. And so they know that during nuclear explosion, there's lots of neutrinos, which is great. So how would you detect neutrinos from the bomb? Clearly some distance away, but you can't put it on the ground, right? Because it can't be that far away. And if it's on the ground, it's gonna get destroyed during the explosion. So they had this idea of this experiment has to be underground to shield it from the explosion. But you can't just dig a tunnel and put experiment there. Because, when the bomb goes off, the entire Earth is shaking. So if it's just underground, it's also gonna get destroyed from just Earth shaking. Okay, so then how do you build an experiment that's truly shielded from the explosion? So the idea goes like following. So you dig a tunnel, and then you suspend the detector. So here it's suspended detector with a rope. When a bomb goes off, you cut the rope. So then the detector will be free falling in the tunnel. So that's the idea. So then it's not touching the earth. So it'll be fine from the explosion. But then you have this free falling detector. So what do? So there's some feathers and foam rubber that's supposed to catch the detector once it reaches the bottom of the tunnel. Definitely the coolest experiment ever. And so this was a proposal for Los Alamos lab. And this proposal was actually funded. And so you might ask, why did we never hear about this experiment? Because, so it was funded, I guess it was gonna happen. Unfortunately, some very annoying people pointed out that, so from nuclear experiments, you get nu E bar. So opposite to solar, we get nu E. So the detection channel for these nu E bars would have been, you get some detector that has proton, which is easy, everything has proton. And there's this inverse beta decay channel where you measure the outgoing positron, and that's it. So they knew at the time, Reynolds knew that, of course, you get the same neutrino flux from just a nuclear reactor. But the problem is nuclear reactor is a steady source, and anything would have produced this positron. So you can't really identify the signal out of the background. So that's why they want to go with a bomb, because then the flux will be huge. And some very annoying people point out that that's when that people just start to be able to detect neutrons at the same time as positron. So that this coincidence detection idea was fairly new at the time. So then they were like, oh, hold on, you can actually do this detection channel and measure the neutron at the same time as this positron, so you get a coincidence signal that will cut down the background. Which means a steady reactor source would have worked, and you no longer need a bomb. And so that is the actual experiment that Reynolds built to measure reactor neutrino, which is why you've never seen this. But still, I just really want to talk about it. So here is it. Okay, so I guess the lesson from this is don't be uncool. Okay, so that's all I want to show, mostly just this solar plot and the atmospheric plot. Okay, let's stay on there. And now back onto the board. So this morning we talk about, how neutrinos oscillate in vacuum, and then we start talking about matter effect. And again, the expression I write down, which is very easily solvable, is when we assume constant matter density. But matter effect is really just measured in solar neutrino oscillation, where the matter density goes like as a function of radius, because as neutrino propagate, it propagate from the center of the sun to outside of the sun, and it's really more like an exponential thing. Which means this constant matter density definitely is not a good assumption. So to actually solve neutrino oscillation in the sun, the actual numerical equation is too complicated. So we'll just see this schematically. The way we typically see it is plot things as a function of density, which means going from the production point to outward, you should think about going right to left in this axis. And the idea is, so when we write down the neutrino mixing, so we say flavor eigenstate and mass eigenstate are related by this mixing matrix, which has some angles, so which is contained by a mixing matrix of some angle. We write this in vacuum, right? And the whole point about matter is when things are propagating in matter, the Hamiltonian of the neutrinos and the Lagrangian changes. So one way to think about it is if we want to plot, which means the effective mixing, or people typically write as mixing angle in matter, now depends on the density of the electron. So effective mixing, which is, again, which you can see from there, the angle or the amplitude term is changed from just naive sine squared 2 theta. Which also means if you diagonalize the matrix, then your mass eigenstate, M1 and M2, now depends on number density. Okay, so let's assume this is 0. If we plot the mass eigenstate, then in vacuum for solar, let's say 1 is M1, 1 is M2, like this. Now things would change as a function of the solar density. And it changes kind of like this. Okay, so okay, that's not good. I want this straight line to align. Not quite aligned. Okay, that's better. It looks something like this. Again, just can only explain schematically. And so for, let's say, for solar neutrino at high energy, so high, or say 10 to 20 MeV, when the neutrinos are born, the mixing angle is actually completely saturated at 90 degrees. Yes. Okay, this means when neutrinos are produced as nu E, they're actually completely aligned with M2. So again, normally the whole problem of neutrino that they change flavor is because the mass and the flavor bisons are not aligned. In matter, in the center of the sun, they're actually completely aligned. So neutrinos are produced, yes, 100% as nu E flavor eigenstates. At the same time, 100% as nu2 mass eigenstates. And then as neutrinos propagate, mass eigenstate don't change, right? So a nu2 is not gonna go to nu1, especially when the mass separate is different. It is large. So then they will just be completely propagate along nu2. So actually for solar neutrino, for nu E, in the two flavor approximation, which again works pretty well, they're actually always propagate as mass eigenstate nu2. There's no oscillation in that sense. There's no jump between nu1 and nu2. Yeah. Right, so between nu2 and nu1, just because we know 2 is heavier, but the principle would be identical if, say, nu E happened to be entirely along nu1. Then it would just propagate entirely along nu1 and comes out to be this. So in that sense, 2 and 1 are not special. It's just 2 is the heavier one. Which is why earlier we had already seen this plot, which is the survival probability for solar neutrinos. And that's why it's sort of flat here as well, because for anything here, they're always produced as a function at M2 mass eigenstate. So then the oscillation probability further does not depend on baseline, because if you're at nu2 mass eigenstate, no matter how long you propagate, you're always going to be at nu2 mass eigenstate. And this whole framework to compute oscillation with varying matter density goes by the name MSW effect. Mikhail-Smirnov, Wolfenstein effect. And solar neutrinos is this kind of thing is the clearest signature we can see it, because we literally see the transition from vacuum to matter. And it will be great if we can experimentally measure this. So far, we have not been able to. But this is the reason that we know that neutrino propagate the heavier one. So we know that M2 is heavier than M1. No questions? Okay, so if not, I want to talk about next generation experiments. So again, if we look at the sort of precision for like mixing angles, for instance, we actually measured them. The mixing angles are pretty precise. Yes. So let's see. Because we have managed to write down the let's see. So we can write down the Hamiltonian in vacuum, which is just like m1 square over m2 square. Hamiltonian in mass eigenstate. And then we know the matter effect in flavor basis goes like this, right? Once you have the Hamiltonian in two different bases, you can like diagonalize them however you want. And then because now you change the Hamiltonian, the diagonalization, hence the rotation between the two bases would be different. And in the sun, I guess I didn't write down the specific terms, but in the sun, it works such that when V is infinitely high, they're just completely aligned. Okay, I don't see other questions. Okay, so for next generation experiments, as you can sort of see from this plot, which actually doesn't do its justice, because in this plot, it seems like we sort of already have some sensitivity to delta CP, but it still shows that it's the worst measured one, right? But actually, because this makes it better than it looks. So right now, we really have no idea what is the value of delta CP, versus we sort of know the other three mixing angles like pretty well. And then another thing that we want to measure is the sign of delta M, let's say 3,2 square, which is of course the same as the sign of delta M 3,1 square. Okay, so let's look at, so what do you need to measure in order to find the sign? So we said the one way to measure the sign of delta M square is to rely on matter effect. So you want the neutrino to experience matter effect in the 2,3 sector. And this is the strategy that long baseline experiment really just Dune uses, which is why the baseline for Dune is something like 13,000 kilometers. So super long. And which is why also, because often for next generation experiment, there's Dune and Hyper-K, and their physics has a lot of similarity. But because Hyper-K baseline is shorter, I don't quite remember, I think it's hundreds. It actually has essentially no sensitivity on mass ordering because this is not long enough. So we really need the baseline to be order 1,000 kilometers. Okay, so that's one way to go, and this is I would say, the easier way to go from a physics perspective. There's another way to go, measure the sign of this is to use just pure vacuum mixing. And I don't want to get into the detail of this unless you want to hear about it, but we can talk about this later. This is a strategy used by Juno. So Juno, one of its main science goals is to go after mass hierarchy, and it uses a completely different strategy from matter effect, long baseline, and which also involves some crazy experimental design. But so I'll just leave the comment there. Okay. And another thing I said we want to measure is the value of delta Cp. And this is intrinsically a three-flavor effect. Is it good with everyone that we would not get Cp violation if there's only 2 flavors? See, mostly nodding. Okay, then I'm gonna say it's good. Okay, so this means if you want to measure delta Cp, we have to be sensitive to 3-flavor effect. And as I said, because this large hierarchy between the mass squares, this is very, very difficult. And so that really sets the design for delta Cp for HyperK and Dune, is that you want to see 3-flavor effect. And also because this is delta Cp, this means we have to see an appearance channel, meaning that alpha cannot equal to beta. Because if there's a disappearance channel, if you're looking at, let's say, the oscillation probability of nu mu to nu mu, you would never see delta Cp. You would never see Cp violation. Is that good? Okay, so what's the condition to see delta Cp, is to see Cp violation in your processes? First, you need 3 generations. Second is you need a process that's like nu mu to nu e. So appearance channel. So this could be different from nu mu bar to nu e bar. But the probability of nu mu to nu mu and nu mu bar to nu mu bar would definitely be the same. So this channel, there's no Cp violation. This channel, possibly Cp violation. That's clear? Okay. So these conditions are pretty much fully constrain the kind of experiment you can do, given finite amount of money, which is how we arrive at the long baseline experiment. So as I said, so first to feel matter effect, your baseline has to be about 1,000 kilometers. We want to see things, at 32 sector. So we know the value of delta M32 square, which sets the energy of these experiment has to be sort of GeV-ish. And then in order to see Cp, you need to see appearance channel. So the process you want to measure is nu mu go to nu e, and nu mu bar go to nu e bar. Because we don't really know how to produce. So in principle, of course, you could also see nu e go to nu mu, but we can't really produce high purity GeV nu e beam. Technically, we don't quite know how. And of course, in principle, you could also see nu mu to nu tau. But it's very hard to detect nu tau at GeV energy because tau is heavy. So this is something that we hope to see a little bit, but with not too much statistics. So this is really like the only options left. Okay, so then let's just write down, okay, then for something like Dune, which is where you can assume constant matter density. The actual oscillation probability, approximately, from nu mu to nu e, looks something like this. So I just want to let you see what other terms that with key information. So a bunch of angles. And whenever mass enters, let me erase this. They always enter as delta m squared L over 4e. So I'm going to call this capital delta. So delta 3,1. Delta 3,1 minus VL over 2. Oh, delta 3,1 minus VL over 2. And this V is the matter potential. So this is the first term. I'm missing a square. And there's a second term. That's not correct. Sine 2, 3, sine 2 theta 1, 3, sine 2 theta 1, 2, and then this term. And keep multiplying. Delta 3, 1, delta 2, 1. I'm running out of space, so I'm going to continue on from this line. Multiply sine VL over 2, VL over 2, cosine delta 3, 1 plus delta CP. And not interesting. Okay. So this is approximate expression for like a long baseline experiment. What is the oscillation probability for nu mu to nu e, which is, this is the actual correct expression for experimental measurements. So a couple key things. So again, in order to see oscillation, we want, this sort of delta m squared L over E to be of order 1, right? So this capital delta 3, 1, that's something like close to 1. And so you see the matter effect coming with this matter potential that we saw, and it comes with like a VL, which means, and we know that this term is small because matter potential is weak, so which means you want the baseline to be long so that this actually does something, which is why that's to sort of set the scale of like about 1,000 kilometer, depends on the size of this and the size of V. Okay, and then, and let's see, another term I want to see is in this term, together with the matter potential and a whole bunch of other things, that's where delta CP come in. Okay. Okay, so, and also, because this is matter potential for neutrino and anti-neutrino, you would expect the oscillation probability to be different because the V would flip a sign. Okay, so all of these things combined tell you get a mass hierarchy, because the mass hierarchy would be the degeneracy of this sign would get broken because of matter effect. Baseline needs to be long, and delta CP does show up in the probability. So that's kind of the main takeaway. This is also why we don't typically do 3-flavor calculation, because the expression is very long. But for long baseline, it actually matters. Okay. Any questions? Okay, so if not, then I do want to show what the experimental spectrum looks like. So could we switch to this? So you see, for These kind of experiments, you always want to measure what happens with neutrinos and what happens the exact same process but with antineutrinos, because the difference will tell you about potential CP violation. And this is kind of taken from the standard Doom publication, so maybe this is a plot you're familiar with. And this is fixed at 1,000-kilometer baseline. So you plot your interesting physics as a function of neutrino energy. And the first thing you see is there's many peaks. Actually, none of those peaks doesn't really matter too much, because the neutrino beam is roughly from, let's say, 2 to 5 GeV. So although the plot go down to 0.1 GeV, there's like 0 event there. So really, you can just focus on the last peak. So that's like a sort of broad that goes from 1 to 10. So just focus on those. And that's, so first you see that actually it is an oscillation. I think this is a sort of like a sine-ish thing. But it doesn't have like a whole lot of feature because it's a pretty broad peak, as opposed to like, there are many wiggles, but there's no events there. And you see that, so this plot where you can see on the left-hand side, the probability is higher. On the right-hand side for antineutrino, probability is lower. That's a result of mass hierarchy. So once you turn on experiment, you see that there's a lot of oscillation in neutrino, much less in antineutrino. You know that's normal hierarchy. If you invert it, these two plots will sort of, left and right will sort of swap. So that's a signature for hierarchy. And then within one of these modes, the different colors show different value of delta CP. So it depends on the value of delta CP, you also get a different precision. So this sort of single sets of measurements will tell you the two remaining unknowns in oscillation. And just to focus on precision, because later when we talk about neutrino detection, interaction is sort of matters. So one thing I think this plot might be slightly misleading is because they use a pretty extreme value of delta CP, like whether it's 0 or 90 degrees, the 3 different lines, 3 different colors look very different. So you might get the impression that, oh, in order to detect these things, we only need to measure the spectrum to like 50% precision, because those are very different. And that's not quite fair, because obviously we want to not just tell the part between 0 and 90 degrees, but measure with better precision. So actually, based on the expected projection, we want to measure delta to something like about 10 degrees. And if you put 3 different lines of like a 0 plus 10 degree minus 10 degree, the lines look a lot closer, and it's about a 5% difference. So roughly speaking, I would think that these are, I would say these are sort of like a 5% precision experiments that we want to aim, which is, again, very, very different picture from like previous generation experiments, right? We see solar neutrino, the oscillation is the effect of 3. Atmospherics, the oscillation is the effect of 2. So there's always a lot of systematics, but they were not as horrible. I mean, I guess except for solar neutrinos, it did, there's a lot of work on systematics. But now with this generation experiment, this is sort of like a few percent precision, which means any theory input come with it would also need to be pretty precise. So that's what we'll talk about later. Okay. Any other questions? On delta CP? So the projected sensitivity is something like a delta CP of 10 degrees. Depends on part of the parameter space, but that's kind of the goal. Mass hierarchy is a much simpler measurement, as you can see, which ones they differ by a factor of 2. So that's like above 5 sigma, no problem. But the CP projection sort of depends on how well we can compute the cross-section, etc. So it's less clear, but that's the standard number is something like about 10 degrees. Yeah. Yes. Um, let's see. That's a great question. Right. I think yes, that is correct. So I think the argument is okay. So when we see CP violation, like in vacuum, then naively it's nu mu to nu e versus nu mu bar to nu e bar. This is the CP conjugate. But actually, because there's matter effect, technically the CP conjugate, so this is nu mu going to nu e in the electron background. So technically the CP conjugate would be nu mu bar go to nu e bar in the positron background. Right. Right. So you're right. So there is that difference from the matter effect because this is sensible. So the difference between this E and so in order to fish out this delta CP, you do have to break the degeneracy between the difference from CP and from V. That's totally correct. Yeah. That is correct. If delta CP is at plus 90 degrees, then the two grains are the closest. Yes. But statistically, or after doing a standard analysis, even if it's at pi plus 2, the difference between neutrino and antineutrino is still significant enough that we can easily measure it with like very, very high significance. But which is why, like when you look at sensitivity projections, they all depends on it. Quite depends on which parameter point you choose. So you can use that to your advantage or disadvantage. Yeah. Good question. So for oscillation physics, unfortunately, whether neutrinos are Majorana or Dirac, it does not show up at all. The reason is okay. So earlier I say, okay, in order to see, PMNS matrix, let's assume neutrinos are Dirac. And then I write down the oscillation matrix to be something like 2, 3, 1, 2, and then 1, 3, then 1, 2. So this is the PNS matrix if neutrinos were Dirac. If neutrinos were Majorana, then you can, repeat the whole exercise. And then the PNS matrix would have additional Majorana phases. And this is the typical convention to where to stick it in, like this. And the other terms are all 0. Because this is entirely diagonal on phases, you can pretty easily convince yourself that they never shows up. They never show up in oscillation. So unfortunately, this is not a answer that we can get from oscillation experiment. Rather, the standard experimental search we use for the nature versus Dirac versus Majorana is neutrinoless double beta decay. So another way to think about it is really the key is lepton number violation. No lepton number violation, very, very hard. Any other questions? Okay, if not, then let's sort of, okay, I think that's all I want to say about standard oscillations. Again, so these are, the theory behind this were established long, long time ago. The main thing is, vacuum oscillation and matter effect, and that's about it. And so phenomenological-wise, there's a lot maybe to get familiar with in terms of, okay, what experiment sits at different E, different L, and, depends on which flavor they're detecting, which parameters they're sensitive to. But alternatively, one can ask, is there like no open theoretical questions with neutrino oscillation? Have we, like, as a theorist, answered all the questions? And I would say the answer is definitely no. There's plenty of open questions that people confuse themselves on. And some of them may have experimental consequences that we don't know. So let's sort of switch topics a little bit. And I want to talk about, okay. And I want to talk about what I call subtleties of neutrino oscillation. Okay. And there's plenty of subtleties. You can easily get confused about, do charged leptons oscillate? Do neutrinos from ZDK oscillate, etc.? So I'll just focus on one, because that one I know best and easy to explain, which is about neutrino decoherence. Coherence. Okay, so what is this thing? So in the beginning, we showed the standard, like Wikipedia of neutrino oscillation. And we point out that there's actually at least two conceptual mistakes. First is we start with a plane wave, and then we say that this plane wave is moving at speed of light, which doesn't make sense. And another one is, of course, we assume that they're equal momentum. So both of these can be resolved by a more complete conceptual picture, which is, of course, that when the particle is produced, they're never a plane wave, but rather they're always, because plane waves are not normalizable states, and they're always produced in wave packets, right? Meaning that when you produce a particle, let's say you produce a new E, it's going to have some momentum distribution. Let's say it looks like this. So I'm drawing the momentum distribution of the neutrino when they're produced. Okay, and so this is a normalizable state, which is sort of which solve this problem, because wave packet, they can actually travel at a group velocity. This also sort of solve this, you take momentum to be the same, because the idea is, of course, there's actually a finite distribution, and let's assume things are Gaussian for simplicity, and so this thing has some width, but we know that things are produced, at pretty sharply peaked, so we know the width of the distribution is much smaller than the average. So pretty close to a plane wave, but actually different. And this is well established. So in fact, you actually also did this when you do QFT from, let's say, Peskin. But normally, of course, the point is the distribution is so narrow that we don't really care. So we integrate out over everything, and everything just properly normalized, which is why we still compute things typically in momentum eigenstate. But technically, that step is always there. Okay, so then when I write down the neutrino that's being produced, it's no longer this thing, as I wrote down, but rather it has some, wave packet distribution. So let's go to position space. This means there's some momentum integral. I have to consider all the momentum. Okay. So then this wave packet would propagate, and that's straightforward to write down. Okay, and then you can, just be a little bit more careful when it's the same derivation as the oscillation probability as we did before, but now you want to integrate over momentum distribution. And so using this, you can compute the oscillation probability. Now it really goes as a function of L. And we're still doing the two-level system just for simplicity. So again, so for earlier, it looks like a sine square and sine square. Right? So now with this wave packet thingy, it got changed a little bit. So it still starts with a sine 2 theta square. So it's the same as the vacuum case, the normal case. But the second term, the one that delta m square, changes. So now it becomes half minus half cosine delta m square L over 2e. So it's quite similar, but then this term is multiplied by exponential minus L over L coherence square, and some other term that is not important. So this becomes the full expression. And so, okay, so this is the same. This is very similar. But now you see I have definitely a new term that is exponential damping as a function of L. And I had this thing. So L coherence, what is this? L coherence is some numerical factors, E square. Sorry, let me just move it down a bit. L coherence is some numerical factor E square over delta m square, sigma x. So what is sigma x? So we start with the momentum distribution. And if we assume things are Gaussian, then, you know, momentum and position is 1 over each other. So we can just assume it's 1 over sigma p. So, you know, this is just the wave packet size of neutrino in position space. So actually, this becomes the oscillation probability. And just vacuum, I'm not, you know, this has nothing to do with matter. The only thing I'm introducing is treating neutrinos realistically as a wave packet as all particles need to be. Any questions at this point? Of course, we're gonna talk about, okay, let's talk about how to understand this first. Okay, so the conceptual picture of this is actually very, very straightforward. So let's think about in position space. And let's say I want to see how much nu E has changed into nu mu. Let's say I want to see this. So rather than thinking that this thing is produced as nu E, I should think about, oh, I produced a nu 1 and nu 2, right? And of course, these are wave packets, so they must have finite, you know, finite extension in space, so they're like this. And my idea is when they're produced, they're obviously on top of each other. So imagine these two are completely overlapping. So this is at t equals 0. And then now these neutrino propagate. Okay, so first, when wave packet propagate in vacuum, the first thing is they broaden. But between these two, so nu 1 and nu 2, I mean, they have different energy, different momentum, different mass. So they're going to have different velocity. So let's say, okay, so here. So let's say after some propagation time, so nu 1 is lighter, then let's say it propagated faster. So this is nu 1, and this is nu 2, meaning that, you know, they're a bit more separated. Okay, and now if you let them propagate for a very, very long time, they're going to be completely separated. Right? Okay, and the scale, so this coherence length sort of indicate the scale, length scale with which they start to separate, like at appreciable amount. Okay, meaning the following. So if we, okay, so let's add one more, sorry. Let's say if things are, pretty, very, very close to here, then things are completely not coherent, have not separated. Then the oscillation length, so at first, is much, much smaller than coherence length. Then looking at expression, you can take the limit of L go to 0 over this, then this exponential term become 1. And you do some trigonometry, and you realize that this probability becomes the normal thing. The normal meaning that it's sine squared delta m squared L over E, which is, again, the familiar expression. This regime is also pretty easy to describe. So let's say you propagate really, really long distance. So then this propagating distance is much larger than coherence length, which is also easy to take the limit. L is much larger. You have exponential of minus very large number, which is 0. You kill this term. So there, the oscillation probability becomes just half with the angle. You also don't have this L over E dependence. So just to be clear, let's attach this sine squared term. So this means, you see, since we know that this worked obviously super well for all terrestrial experiments so far, this means we're always setting up our experiment to be in this regime. Because, the largest baseline we can have is about 1,000 kilometers, or most, size of Earth. We can't go much longer. So we're always in this regime. And now you might say, well, what about neutrinos from like ice cube? Because certainly that baseline is not long enough. So for ice cube neutrinos, have we reached this regime where, things become like this? And unfortunately, the answer is we'll never be able to tell. We don't know. Why? Because for ice cube neutrinos, this may happen, this may not happen. But what we know for sure happens is this, what I said earlier, average over L, right? Because it certainly extends the source. And if you remember the consequence of averaging over L, you also get into this, this turn to half. You also get this, just the amplitude. So for any astrophysical neutrinos, we never have any information or energy or L dependence or delta M dependence information. And you always just get some like a fraction of events. And we don't know whether decoherence have happened or it's just averaged out. So experimentally, we can never test this. At least no one has come up with an idea to test it so far. Okay, so then obviously the most interesting regime is here. Because the idea is could just take our baseline a little bit longer for somehow, then we could see this, very weird dependence. So we have some cosine of L and with the exponential of minus L squared, which will be a very distinct signature from this guy or this guy. So it will be great if somehow we can see this. Okay. And the argument, of course, is since so far we have used the left expression and nothing ever goes wrong, then presumably we're just, we can't do the middle one. But actually recently there has been claims contradicting that. The statement goes like the following. You see this L coherence, it depends on energy square on top. And it then depends on delta M square on the bottom. Okay. So this means if I have a larger delta M square, coherence length will be shorter. So I'm more likely to be possibly observe this. And recent claims are the following. So that for delta M square, again, we know we have the two standard model ones, the solar ones, which is something like 10 to minus 5 EV squared. And then we have the atmospheric one, which is 10 to the minus 3. And the claim is that, okay, for these two, not light enough. But we also have this tentative signal of this 1 eV square, right? So you see, for the claim is that for if this 1 eV star actually existed, then this number will be large. So then we will get a smallish-ish L coherence length. And actually, the statement is that this would actually be comparable to actual baseline of the experiment, which will make us being in the cosine times exponential is like a very interesting regime. So this is the recent statement. And actually, the statement that there's some data in current search for this 1 eV that favor this scenario. Okay, so what's the question? The question is this real? Is this correct? How will we know it's correct? We want to know what is L coherence, right? That means looking at this expression, we want to know what is E square of the neutrinos, and that's easy. We always know what that is. We want to know the potential delta M square, which let's say it's 1 eV square. And then it seems like we just need to know the sigma x. So in order to sort of test this, we need to know what's sigma x. And as it turns out, we have no prediction or understanding on how to compute the sigma x for any realistic sources. So complete unknown. Which also, of course, means that even for the standard model oscillation, we don't know what is the appropriate L coherence. Let's say maybe it's sort of on the boundary of detectability. We just need to build a slightly longer baseline, but you wouldn't know because there's no prediction. Okay, and why is there no prediction? Okay, so for instance, there's many estimates for reactor neutrinos for this quantity. Goes like the following. So we want to know reactor neutrino, which is from nuclear beta decay. So we want to know the sigma x for reactor neutrinos, roughly what it should be. Well, so one possible suggestion is that it's kind of like a uncertainty principle, right? We want to know the uncertainty or the spatial extent in the position, which should roughly go as the uncertainty, energy. And reactor is pretty like a broad, so the uncertainty on the width of the energy spectrum is roughly its energy, meaning that this is something like MEV. So this seems reasonable. But then there's other arguments. Because we know these neutrinos are from nuclear beta decay, and nucleus is a big thing. So the spatial extent of the neutrinos must be like the size of the nucleus, because that's where the neutrino is from. So another argument is this is the size of nucleus. Okay, that also seems reasonable. And then another argument in literature goes like, well, so in the nuclear reactor, things are very dense, and there's plenty of nuclei there, and you don't really know the exact position of the nucleus. As it decays, right? So they say it's not really the size of the nucleus because you don't know where it is. So rather, it should be how well this mother nucleus can be localized, because then that's where you know where the neutrino is from. So which sort of corresponds to mean free path. Of these nucleus. So these are all the arguments in the literature that sort of advocate for the size of sigma x, and naively they all kind of make sense, or you can also argue they all don't make sense. But the issue, of course, is that, say, using these few scales and some other choices people have proposed in literature, the value of sigma x range from 10 to the minus 5 centimeter to 10 to the minus 12 centimeter. So it's like 7 orders of magnitude. And the reason of, I mean, there's just many scales in the system, right? And it seems like there's many arguments to support one scale over another, and they all sound at first like, reasonably plausible. But of course, this, I wouldn't call this a prediction, right? You spend 7 order of magnitude, and remember, this is a thing that's gonna end exponential. So even a factor of 2 could really affect whether things are observable or not, let alone this big. So within this range, it can go from, this effect completely not observable to this claim that this could be observable in current or future experiments. So that's all in this range. But that doesn't mean much because it's very big. So this is, I consider, a super concrete problem because this, because like for a lot of these subtleties, one of the maybe criticism is, okay, this thing will never be observed. Let's say whether the neutrinos from Z would oscillation would not. At least we don't have current experimental setup that will measure that. But this one's very concrete because if this happens, then you would actually see even in like current setup that the oscillation probability would have some, very different or mildly different behavior in L. And it all hinges on a very well-defined quantity because we know everything about these neutrinos. We know that they're from, let's say for accelerated neutrinos, we know they're from pion decay. We know everything about these beams. Or nuclear reactors, at least in principle, we know all the things that go into there. And if you think about it, there is no, at least to us, there's not any framework from, quantum mechanics or QFT textbook that would allow you to compute this. At least none that we find. So I challenge you to think about if you can come up with any way to calculate this quantity, because I think it's just really well defined, and yet we can't seem to be able to compute it. Yeah, good question. Because let's say in this thing, because we know every other term, presumably with some reasonable precision, so are we allowed, can we? And the answer is not so far because we have not observed essentially the effect of this term. What this allows you to do is, of course, put a limit on this quantity, or sigma x, and that is indeed what experiments do. And I think the leading constraint comes from reactor experiment, and that's close to the boundary here. So it hasn't, let's say, disagreed with theory estimates yet. And with next generation reactor experiment, Neutrino is going to be able to push it further. But sort of this tentative hit of like this 1 eV oscillation, it's right about at this boundary. And there's actually some other recent experiment that they just set out to look at. It's not an oscillation experiment. It's just a basic experiment where they try to measure they try to set a bound on the sigma x of neutrinos. And even there, because we really don't know how to relate things, even with a very, very precise and dedicated experiment with measured signal, their bounds on the neutrino sigma x still vary by a bunch of order of magnitude because they don't know how to interpret the results. So regardless of the measurement, it would definitely be great to understand what this quantity means. Good question. So I think the argument in the literature roughly, it does not work more in detail than sort of this relation. So you can imagine this is the distribution of energy for the entire energy beam. And of course, you can imagine that it's different from the energy distribution or energy width you would think for one event. But then how do you estimate that one is still, yeah. Okay, so this is sort of what I consider a subtlety. Maybe it's not so subtle. I think the problem is pretty straightforward. The solution's definitely subtle. Sort of between this is where really people argue about which one's correct. Again, if you have ideas to compute this, definitely that's great to clarify this. So that's one of the questions. Another one is a very simple. So if you want to try to write a project on, let's say, neutrino oscillation, another very straightforward idea is for those of you who are very good at coding, is you see for three flavor oscillation, I was able to write down expression. And in principle, if you want to compute this numerically, you just diagonalize a 3 by 3 matrix, right? So in vacuum, this is very straightforwardly done. It's very quick. And in matter effect, though, as you see, you have to diagonalize the matrix with some varying, density, which is still, I guess, not that difficult. It's really just diagonalizing 3 by 3 matrix, but with some vary parameters. But actually, the computation of just computing this oscillation probability is a huge, let's say, bottleneck or a leading computation cost in actual oscillation experiments. Of course, the reason is you do one time, it's very fast. But for an experiment to do this, of course, you can't just do it one time. You want to vary experimental systematics. You in many, many different ways and do it thousands or tens, whatever, many, many, many times. So actually, for realistic experiments, especially where they expect the matter effect or go through Earth, etc., this is a huge, it takes months to scan these oscillation parameters, which is why there's actually a lot of effort going into just speed up these calculation. Again, there's nothing theoretically new. It's literally just solving a numerical problem. And so if you're very confident in your numerical capability, you can try to write a code and see if it's faster than any of the codes available on the market. It's very easy to search, search neutrino propagation fast. I think the latest code is literally called new fast. So you can try to search, you can try to write a code, see if yours can beat new fast. And that would be a significant contribution to experimental program. Any questions about that? Or any immediate ideas? I mean, personally, I never really appreciate this problem, even though I know it was, I always know it's a major cost for experiments. But because I didn't scan much parameters, so I thought, whatever, a slow code would work. And then recently I started doing some simple parameter scan. And even at the pheno analysis level, it's disturbingly slow. So a faster code would definitely be very useful for many things. But I think it's pretty hard to beat new fast. Okay, any other questions? Yeah. Great question. So the short answer is we actually can't ignore it. So the reason, which we'll talk about this next class, is so there's a whole lot of search going on to study this 1 eV stereo. And this has been going on for 20 years, and this has been searched in at least 20 experiments, 30, maybe 30 plus. And the reason that why the situation is so murky and we're still trying to understand it is because obviously we would really, really much appreciate to get a consistent picture from different experiments, right? So the 1 EV situation roughly can be summarized as a bunch of experiments have seen weird things that we can't explain with standard model. A bunch of other experiments have see things completely consistent with standard model. And each has like more than 10 experiments in their category. So which makes it very hard to understand what's going on. If the signal is real, then why are a bunch of things not seeing things? If the signal is not there, then why do like 10 different experiments with completely different setup, with completely different systematics and different channels, all see things that sort of point to roughly the similar region of parameter space. So it's very confusing, which is why, of course, people work on individual experiments and trying to understand the situation. But also, we want to understand the tension between different experiments. And that's sort of where the claim first came up. It's that, so reactor experiments, it is a big class of experiments that are trying to test this 1 EV. And even between different reactor experiments, which, there's already some canceled systematics, they still see, people still disagree with one another, which is very, very strange. So the claim is that by fitting this expression with, with a number, at least that's in this range, you're actually alleviate the tension between different experimental data sets, which really, which means to me felt like this is something that we have to address, because otherwise we don't know how to, like with 10, let's say 10 experiments seeing signal, 10 experiments don't see signal, how would you ever resolve it? And then just also a quick like aside, of course, I posed this question because this is something that I'm very interested in and I'm currently working on it. But we're pretty confident in the following scaling. So this signal was, this decoherence effect was initially proposed in this 1 EV. Now, you might be a non-believer for this 1 EV signal. Many people are. Then you say, well, I really don't, I just don't believe the 1 EV signal is real. Then I can just ignore that. But what we find is that if the signal, if the width is really sort of around here, then you will see that this would not only show up for this 1 EV oscillation in reactors, it would also show up in just standard, the atmospheric mixing. So it would show up in dune as well, because things sort of scale in a similar way. So if it's really like around here, then this is something that would just show up in standard 3-flavor neutrino mixing, and it's definitely going to affect how we extract, let's say, delta CP or other mixing angles. So that I'm pretty confident of. So I think this is something that we at current experimental precision, we definitely want to resolve it one way or another. Yeah. Very ambitious. Sigma X. Oh, sigma X. Great question. I never really thought about it. I think the first question that probably worth noting is that this sigma X, this is the wave packet distribution of neutrinos at production. So important thing is different sources would produce completely different sigma X, right? So here, all the argument is this is specific to reactor neutrinos. So, like nuclear stuff. Which means, for instance, you were to think about accelerator neutrinos that's from proton producing pion, then pion decay, you will get a different scale, completely different numbers. Presumably that's determined by something about pions. This is determined by something about nucleus. So then if we think about C nu B, the wave packet size of C nu B would be determined by, I don't know, neutrino decoupling or some other cosmology effect. So for that perspective, even if we had measured sigma X for one system, we still have to, it should be completely uncorrelated with a different system. In that sense, not directly translatable. And second, I never thought about it before, so I have no idea whether measuring C nu B I guess it's also what you can measure about C nu B. Can you just measure the rate or energy distribution or angles? That what would that tell you about sigma X? Just no idea because I don't know. I haven't really thought about that, and I don't know like a specific experimental design that would guarantee the detection. Any other questions? Right. Yep. Uh-huh. Yes, so I would say there the question is you're okay, so it doesn't solve the problem, it sort of push the problem to a different place. So what you are talking about is actually a typically called like the QFT treatment of neutrino oscillation, meaning that as opposed to what we did today, you just treat neutrino production and detection as a giant Feynman diagram, meaning this is also a very popular, so idea is, let's say we want to study nu mu to nu e. So really what this means is you have a, let's say a pion decay that produce a muon and with a neutrino, and then this muon neutrino would propagating, and let's say this turn into nu e, so you detect it with, I don't know, that okay, neutron, proton, neutron. So down. Okay, so let's say you have a down and electron and up. I think I conserve charge, but you get a point. Okay, so the idea is, of course, you don't, so this is tackling neutrino oscillation, but you don't have to consider this, right? You can just treat this as left part of the diagram with a very, very giant propagator and then right part of the diagram. And then this is a very popular approach. And actually this, so this has its, subtleties and conceptual confusion on its own. And also how to map this picture into the quantum mechanics picture. So there's, lots of activities here. But the point is, sure, if you do this, you don't need that. But then you still need, let's say, when you compute this pion cannot be in a plane wave, right? Technically, you cannot just integrate over like what you do in Peskin. So then this pion would have this similar momentum distribution as a function of momentum, and this is the sigma p pion, which of course you can relate to sigma p of neutrino and sigma x. But what is this? Like, how do you? Well, that's like how, like I can tell, in let's say for Dune, it's you have an AGV proton beam hitting beryllium. What is sigma p of pion? Like, how do you model it? Right. So it's not. We still don't know, right? So actually, so you can perfectly so relating this is not too terrible. You can definitely relate the property of pion to property of neutrinos, but then it's like you just delay the problem. So there's some so there's some conceptual match you have to carry from the quantum mechanics to QFT, but the issue of this initial particle momentum distribution or position distribution in wave packet picture is unknown. It shows up in any language, like a AGV proton from a hydrogen tank circle a couple times produce pion. So how do you compute this? I see a hand here. Yes, that's true. We should follow a Boltzmann distribution. Yes. And how does that translate to this? Well, I would say first, I'm not sure because these pions are like, I guess, highly non-thermal. I mean, these are hard scattering processes. And the proton, I don't know much about the proton in a collider, but I guess you can almost treat the proton as entirely like monoenergetic. And then it's not like I don't think Boltzmann equation would work here. At least it's not obvious to me how you would do that. Good point. Yes, I think something like that in principle should be closer to what people have tried so far. But I think the key there is to come up with some sort of even conceptual, like actual experimental design. Because how would you, like, what would you try to entangle and how to do that like realistically? So, like, as far as I know, for instance, this definitely has a lot of recent attraction. And then the only experiments that I think were done had some measurements that reported some results. Was this what I mentioned? They are using. Okay, I think they're using some sort of electron. It's like a beta decay. So I don't remember what exactly nuclei. Some combination, some sort of lithium or beryllium. So like they have. So you want to produce a neutrino. So this is the measurement they use. And then you want to measure the sigma x of this thing. Or let's say you want to measure the sigma p of this thing. And of course you couldn't because, that requires a giant neutrino detector. So what they measure is they just measure the recoil of this beryllium very, very well, which is very difficult. And then they think that they have measured the momentum width of the beryllium. And actually they give a definitive number here, which is already very impressive. But even then, this is like seems incredibly difficult. They didn't quite manage to do so concretely to translate this number into a value on sigma x of neutrinos, because they don't quite know how. So they tried a couple different assumptions, and results differ by like order of magnitude. So even with a very, very impressive experiment, they couldn't really measure this quantity. So I think here the confusion is that you don't know what this actually meant. So something like a Balancing inequality, I think maybe interpretation would be a bit more straightforward. But like, how do you actually set up experiment with finite cost that does that? Okay. Any other questions on this or any other neutrino oscillation related questions? Okay, if not, then I think we're at about 1.5 hour mark. So that's all I want to say about neutrino oscillations. Happy to take any questions. If you're interested in Juno experiment, which has a lot of recent activity, then happy to talk about Juno design, which is very different from the kind of matter effect delta CP in long baseline. But the takeaway, hopefully, is that the standard oscillation derivation is pretty easy to look up, and matter effect from a theoretical perspective, at least, is pretty well understood. But don't mistaken that as all problems in neutrino oscillation is resolved. So there's a bunch of things that with certain experimental consequences are still really we don't understand. So for instance, if you have ideas to compute this, would be really, really, really welcome. Okay, so if no more questions, then tomorrow we'll start with stereo neutrinos.